So in this lesson, we're going to be looking at the idea of concurrency. Now, concurrency, the word concurrent basically means things happen at the same time. So we're going to explore the idea behind thinking concurrently, i.e. How do we think about a problem in the way that we want to do things at the same time, rather than serially, which is what we're very much used to the idea of being in parallel, the actual kind of mechanics of it. So let's break this down a little. So let's look at the difference between parallel and concurrency. Now, those words can be interchanged. So what I'm going to do is really make a real big distinction between how we think about problems, so thinking concurrently, and the word parallel, where I almost use it in the sense of this is the mechanics of it. Okay, so a parallel problem is one such that we can break it down into parts. Okay, that sounds very much like decomposition, doesn't it? But there's something very special about it. So each part should be able to run independently of the other parts. Okay, I'll give you an example. Imagine I have a large set of data, okay, and I have to do the same calculation on every single part of that data. Now, rather than just start at the beginning, just go with one over the other, which is very much almost like a linear search, I can just break it up into parts. So I can maybe break into 10 parts, and each part is then done independently. When I do that, I can then do them in concurrency. So it doesn't matter if I do the first 10 and the second 10 at the same time, because I'm just doing the same calculation to each of them. So they can be running concurrently. So I can break down large sets of data into smaller chunks, which can then run at the same time. So that's one of the classic ones. The key to parallel problems is that we have a situation where different parts of the program or problem can be run independently of one another, which means that we can process them at the same time. So another example might be where you've got a computer game. Now in computer games, they can be quite easy to make threaded in some ways, because you might have one thread which is kind of drawing the screen and just redrawing it, and another thread working out the AI behind the scenes. Now, as long as those two sync up in enough of a way, we should have a situation where the AI can be running in the background while the scene is drawing maybe on the graphics card. So thinking concurrently is kind of how we tackle these problems. So if I have a problem such as I need to calculate prime numbers, okay, all the prime numbers between 1 and a million maybe, I can think of that as a serial problem. So I'll start on number 1, then 2, and I'll just check every number until I get to a million. That's very much a non-concurrent way of thinking about it. A concurrent way of thinking about it might be that, well, okay, well, I'm going to check the first 100,000 numbers on maybe as one computing unit, then I do the next 100,000 on another unit, and I split it up into 10 sections, okay? And then each section can be run on a different core at the same time. So that's what I mean when I say thinking concurrently. Now, concurrency, parallelism, we need a practical way of doing it. Now, when thinking concurrently, we want to make sure we're thinking in the right way. And this is not anything formal, okay, it's just a way I like to think about concurrency. So I see them as 3 kind of different groups, okay, as a most basic idea. A data-driven group, a request-driven group, and activity-driven group. So what do I mean by this? Well, if something's data-driven, it means we have a large set of data, and that data can be maybe done independently of one another, so they don't rely on each other. So for example, the prime number one. I can break that chunk of data into parts, and each part can run concurrently. I might be request driven. Now this is quite a common one, where we might have a website. Our website might have loads of users coming in at the same time, and because of that, each one of those requests could be considered as a unit of work. Now, because we have all these distinct unit works all coming at the same time, we've got a chance for concurrency. Okay, so I might have 3 requests come in, and rather than doing 1, then 2, then 3, I can do all 3 at the same time. Okay, sorry. Then activity driven. This is where we have a program or a problem where we can split it up into different parts. Now, those parts may not be the same thing. So, for example, drawing a scene and AI. But I can split it up, and those parts can work at the same time. They can run concurrently. Okay, those kind of problems are actually more common because in some programs there's some things that can run behind the scenes. I'll give you another example. When I create a PowerPoint and I want to narrate it and then turn it into a video, what happens is the encoding of the video, turning the PowerPoint into a video, that happens in a thread, okay? And you get a little bar at the bottom of the PowerPoint saying, I am turning this into a video. I can still use the rest of the program. Okay, so the one part of the program is running as a thread behind the scenes, doing that encoding, whilst the rest of the program is free to do something else. If that was not the case, what happens is the complete program would just freeze until the video had been encoded, which is obviously bad user interface. So, although this is not part of the course, it's actually quite an interesting thing to look at. We're now going to explore this idea of threading. Okay, now threading is the practical way we can code our programs to actually allow us to think concurrently and enable parallelism in our code. So threads can be run in parallel. Okay, so what we can do is we can create these threads, and they're going to be distinct compute units, and we can then tell Python just to run these threads, and then they will manage which threads run when, all independently for us. Long short of it, kind of uses its own scheduler to be able to do this. And the nice thing about it is that it will genuinely run on different cores, so we can actually see that. So what is a thread? Well, this is, as I said, the practical way of actually doing concurrency. So a thread is a self-contained unit of work. Now remember, when we're thinking concurrently, we're thinking about a single unit of work that can run independently. Okay, it cannot be reliant on something else. It has to just run on its own with no interruptions. So that is what a thread is. Threads are designed to work independently of one another, but there are times where we may want to send messages between one thread and another, and they can do that, okay? However, if they have to send a message and have to wait for a message before they can continue, well, then you're going to lose some of that advantage of concurrency. So you try and avoid that as much as possible. So they do run concurrently, they run in parallel. They are managed by the operating system, so you have no control over the order the threads run, but that's okay because they're running independently. If they didn't run independently and we did care about the order, well, actually we're now talking about a serial approach, so threads wouldn't work anyway. Threads can communicate, they can wait for other threads to finish, they can use something called mutex locks and semaphores, which is massively outside the scope of A level, but if you are interested, please do research it. It is quite an interesting topic. And they don't share data with one another, okay? Unless you really must. Now, it's very important that you bear in mind if two threads are trying to access maybe the same variable, you're going to get an issue. We're going to talk about that in a bit. So let's look at some of the practical implications of this and actually how to code this. So the first thing in Python, if you want to do a multi-threaded approach, you need to import threading, okay? So this is the library that you require in order to be able to do this. So the next thing you need is the worker thread. Now in Python, the easy way to do this is by creating a function, which is going to be your compute unit, okay? This function should take in some parameters, okay, the information it's going to work on, and then independently go through and produce an answer, okay? It's very important that it's not sharing information with other functions, anything like that. It just simply runs. As soon as the work is finished, i.e. the function finishes, the thread dies and no longer runs, okay? So the thread is essentially just running a function. Then you have to create threads. Now, in order to create a thread, you need to use the .thread thing, so the threading.thread part. You need to pass through a number of bits of information. So the first of all, you need to pass through the function you want to turn into a compute unit. So in this case, it's display prime numbers. And then the arguments you want to throw. And these are going to be the parameters for the function, so the input to it, essentially. Okay, so the example that I showed you just now has three parameters. The first one being the thread name, so this is just a number I've given it so we can actually see it when it outputs, and a start and end range, and this is the numbers that we're going to work on. So as I said before, when you run threads and you maybe have 5 threads, 10 threads, however many, you kind of, as a concept, would think, well, thread 1 would run, then 2, then 3. Well, that makes sense, doesn't it? However, that's not what happens. What happens is the threads run at the same time, which means because of that, you're going to get them out of order. Okay, the order of which thread runs first is completely out of your hands. Okay, which is one of the reasons why it's really important that these threads are independent of one another. Okay, because you have no control of the order. So in this example, you can see that you've got thread 4, then 3, then 2, then 1, then 4, then 3, then 2, then 1. So though it looks like an order, actually there is no order to it. It just happens to look like that. You've got 4, 2, 1, 3 a bit lower down. So you can see there is no real order to it. It's just running it and displaying prime numbers as and when it gets to it. Let's consider the difference between a multi-threaded approach to a problem and a single-threaded approach, or a concurrent approach and a non-concurrent approach. So the problem we have is displaying the prime numbers between 1 and 500,000. So I've got a function here, a really simple one, which is going to calculate whether something is prime or not. Okay, so just taking a single number. Then I've got another function which takes in a start number and an end number. So the start number is where it's going to start looking through, and end is where it's going to end. So it's going to look for a range of numbers, and for each number that is prime, it's going to output that number onto the screen. Now, I'm calling that function initially with numbers 1 to 500,000. And when we run it, we're going to monitor the resources. Okay, so specifically the calls. So here I've got resource monitor, and you can see down the right hand side I've got all the cores of my computer. So when we run this, what should happen is this program will run on a single core. So let's see that in action. So let's run the program. Okay, and let's look at the cores. Now, obviously some of them will start to move because I've just did a few things, but now can you see that they've started to settle down apart from one core. So CPU 3 on the screen you can see is at 100%, and it's now consistently 100%. So what's happening is this program is now running on a single core, and now that it's finished we should see a CPU 3 suddenly drop down, and there we go. So in this example we had one core running all those instructions. Now let's comment that out, and now let's go for a multi-core version. So in order to run this concurrently, we need to split the problem up. So what I'm going to do is I'm using this loop and these two numbers to split up the range of values. So initially it's going to start at 1. So even though it says 50,000 there, we've got I minus 1. Well, I is 1 to begin with. So 1 minus 1 is 0. Anything multiplied by 0 is always 0, which is why this starts off as number 1. Then we're going to have obviously 1 minus 1, which is just 0, and then 50,000. So the first range can be 1 to 50,000. Then we're going to get 50,000 plus 1 all the way to 100,000, and that range number is going to be created. So if I run this program now without actually starting any of the threads off, okay, you can see I've got that number pattern. So I've got these threads all kind of running a different range of numbers. So to create threads in Python, I will use the thread class. Okay, we pass through the name of the function we're going to run, which display prime numbers, and we pass through 3 arguments. Now this time I'm going to talk about thread name. Thread name is just literally the number of the thread. Okay, that way we can tell the difference between the different threads. Then we've got the start range and the end range. So each thread is going to run a different set of numbers, long and short of it. So I'm now going to uncomment these two, because what I've just done is once I've created the thread, I've added it to a list, and then I'm going to tell each thread to start. As soon as they start, it's going to start running. So again, I'm going to run it, and this time I'm going to look at the cores and see what happens with those. So we're going to run the program, and now, if you remember last time, CPU 3 went to 100%, and now what should happen is we have a number of these cores all running at the same time. You can see they're all kind of evening out now. So not every core is, well, none of the cores are 100%, so all kind of doing a little bit of the work, but you can see all the cores are now working together. So each thread is been sent to a different core in order to execute it. and as soon as it's finished, all those calls will then just suddenly drop down again. Now, that is what's happened, but in the last example, what you saw was all the numbers being printed out in order. Now, if you notice that we have thread 4, then thread 9, then thread 4, then thread 9, then thread 9. If we go up a bit earlier, you see the order is very different. I've got thread 9, thread 5, 9, 5, 9, 5. And you can see the order is changing. And the reason for this, maybe go up a lot further, so thread 10, then 5, then 5, then 6, and 10. It looks like a really random order, but what's happening is because these threads are all running at the same time, one might find a prime number before another one, and as such. So concurrency is very, very, very powerful, especially when I've got a large amount of data or a large problem I need to break down. However, we do sometimes have issues. This is where we have to be slightly careful, especially if we're sharing information between two threads or we're getting two threads to work on the same thing. So, for example, what would happen if I had two threads all working on the same list of numbers at the same time? Well, because we can't control which one comes first, and we also have no idea whether these two, because they're running on multiple calls, if they're going to happen at the same time. So if they're trying to update the same value at the same time, which one goes first? This is an issue with concurrency, and it's one that you can solve through mutex locks. However, as I said before, that's out the scope of A-level. What is important for A-level is this idea that we have to be very careful when we design threads and concurrent modules so they don't accidentally corrupt data, i.e. using the same data. So data corruption happens when two or more threads try and access the data at the same time, okay? Especially when we talk about writing. Okay, reading is not so much of an issue because if you read the same data at the same time, well, that's fine, isn't it? Okay, you can always have someone looking over your shoulder while you're reading the book, and you can read the same book at the same time. However, if you were both trying to write the same on the same piece of paper at the same time, it's just going to get a big mess and you're going to get in a big argument, aren't you? So when two or more threads try and access or write data at the same time, or even when one's writing, one's reading, we may get data corruption. This is why we have to introduce locks. Okay, so although locks are outside the scope, what isn't outside the scope is this idea of corruption of data when two write at the same time.